Hey everyone, welcome back to Singularity today. I'm Atom Infinity, and today we're going to dive into some mind-blowing research from the world of artificial intelligence. From robots learning to mimic human actions, to new ways to understand and explain the decisions made by complex AI systems. This week has seen some incredible advancements. We'll be discussing cutting-edge breakthroughs in areas like 3D modeling, natural language processing, and reinforcement learning. Buckle up, it's going to be a wild ride. In the research titled Vista 3D, Unravel the 3D dark side of a single image, the authors tackle the challenge of reconstructing a 3D object from just a single photograph. They present Vista 3D, a framework that efficiently generates 3D models in a matter of minutes. Vista 3D employs a two-phase approach, a fast coarse phase and a refined fine phase. The coarse phase quickly creates an initial 3D shape using Gaussian splatting. Then, the fine phase extracts a signed distance function, STF, from the learned splatting representation, refining the 3D model using a differentiable isosurface. Additionally, Vista 3D utilizes a disentangled representation, separating the visible and hidden parts of the object, resulting in a more comprehensive 3D model. Through extensive experiments, Vista 3D demonstrates its ability to generate consistent and diverse 3D objects. This research has the potential to revolutionize 3D modeling, offering a quick and efficient way to create 3D content from single images. Imagine using a photo of a chair to instantly create a detailed 3D model that could be used for virtual reality, gaming, or even 3D printing. The research opens doors to exciting new possibilities in fields like virtual reality, computer graphics, and even e-commerce, where 3D product visualizations are becoming increasingly common. In the research titled Dynamo, in Domain Dynamics Pre-Training for Visual-Motor Control, the researchers tackle the challenge of training robots to learn complex tasks by observing human demonstrations. The problem is that existing methods often require a huge amount of data, like hundreds or thousands of videos showing the task, to teach a robot how to do things. This is because the robots struggle to understand what they're seeing in the videos. The researchers propose a new technique called Dynamo that helps robots learn from images better by focusing on the way things move in the world. Imagine you're learning to play basketball. Instead of just looking at pictures of people playing basketball, you would learn better by watching videos of them dribbling and shooting the ball, right? Dynamo works similarly by helping the robot predict how images will change in the video. This allows the robot to develop a better understanding of the environment and perform tasks with fewer demonstrations. The research shows that robots trained with Dynamo can learn new tasks more efficiently and achieve better results. The results hold across different types of learning methods. This research could have a significant impact on the development of robots that can learn new tasks quickly, like robots that can help with household chores, factory work, or even healthcare tasks. In Quint2Vel, Enhancing Vision, Language Models Perception of the World at Any Resolution, the researchers introduce a new model called Quint2Vel that tackles the issue of handling images of varying resolutions in computer vision. This model is designed to analyze images like humans do, adapting to different sizes and details without any predefined rules. Quint2Vel is a big improvement over previous models and can work with images and videos. The researchers show that by increasing the size of Quint2Vel and feeding it more training data, its performance gets significantly better. The largest version of Quint2Vel 72 parameters can achieve results comparable to some of the top models like GPT-4o and Claude 3.5 Sonnet across many different tests. This research showcases the power of large multimodal models, paving the way for more advanced AI systems that can understand and interact with the world in a way that's closer to humans. Quint 2 Veal can be helpful in many applications like image understanding, object recognition, and even generating captions or descriptions for images. Imagine a system that can automatically describe the content of a photograph in a comprehensive and accurate way, or a smart assistant that can understand what's happening in a video and provide relevant information. In the research titled "To Cut or Not to Cut," Chain of Thought helps mainly on math and symbolic reasoning. Researchers investigated how effective chain of thought prompting is for boosting large language models' reasoning abilities. They looked at over 100 research papers using this technique and conducted their own tests on various datasets. The key finding is that chain of thought prompting COT is most helpful for tasks involving math and logic, like solving equations or deducing conclusions from given information. The research found that COT provides a significant advantage in these areas, but it's less effective for other types of tasks. For example, COT didn't make much difference on a general knowledge test called MLU, unless the questions or answers involve mathematical operations or symbols. The researchers also explored how COT works by separating the problem-solving steps into planning and execution. They compared COT with language models that use tools like symbolic solvers and found that COT excels at improving symbolic execution, but falls short when compared to using dedicated solvers. Overall, this research suggests that chain of thought prompting can be a valuable tool for boosting reasoning skills in large language models, particularly in areas like math and logic. But it's not a universal solution for all reasoning tasks. The research also highlights the potential for developing new approaches beyond prompting to fully leverage intermediate computation in these models. Imagine you're trying to explain a complex recipe to someone. Sometimes listing the steps one by one is the best way to do it, and other times you might be able to show them a picture of the finished dish or give them a shortcut. This research is akin to figuring out when each approach works best. In the research titled Computational Dynamical Systems, scientists explore the computational power of smooth, finite, dimensional dynamical systems. These are essentially systems that evolve over time according to smooth mathematical rules. They investigate whether these systems can simulate Turing machines, which are theoretical models of computation that can perform any possible calculation. The research finds that chaotic dynamical systems, which are known for their unpredictable behavior, and integrable dynamical systems, which are more predictable, are unable to reliably simulate universal Turing machines. However, other types of dynamical systems can simulate these machines. The researchers also discover that if a Turing machine can be encoded into a stable, one-dimensional dynamical system, then it must have a decidable halting problem, meaning there's a way to determine whether it will ever stop running. This research also reveals the importance of carefully defining the encoders and decoders used to translate between the dynamics of the simulation and the system being simulated. This research highlights how the concept of a computational dynamical system bridges the gap between computational complexity theory, dynamical systems theory, and real algebraic geometry. It opens up new avenues for exploring the relationship between these areas and could lead to new insights into the nature of computation. Imagine using a chaotic system like the weather, where small changes can lead to large, unpredictable consequences, to simulate a complex computation. This research suggests that this is not possible in a reliable way. On the other hand, it also opens up possibilities for using other types of dynamical systems for computation. It could lead to new approaches for designing computing systems that take advantage of the inherent dynamics of the natural world. In the research titled Abductive Explanations of Classifiers Under Constraints, Complexity and Properties, the authors explore the use of abductive explanations for understanding how classifiers make decisions. They highlight a key issue. Existing definitions of X work well when features are independent, but they can lead to a huge number of redundant or unnecessary explanations when there are constraints between features. To address this, the authors propose three new types of explanations that consider constraints and can be generated from either the entire feature space or a specific sample, like a dataset. These new explanations are based on the concept of coverage, which refers to the set of instances that an explanation can explain. The researchers show that coverage is effective in removing redundant and unnecessary explanations. They also analyze the complexity of finding explanations for each type and investigate their formal properties. The outcome is a collection of different types of access with varying complexities and guarantees. This research aims to enhance the interpretability of classifiers by providing more concise and relevant explanations, which could lead to better understanding of complex decisions made by artificial intelligence models. For instance, imagine a classifier that predicts loan approval based on factors like income, credit score, and debt to income ratio. If these factors are interlinked, traditional explanations might generate a lot of redundant explanations. This research offers a way to identify and discard these redundancies, leading to simpler and more meaningful explanations. In the research titled Decoding Style, Efficient Fine-Tuning of Elms for Image-Guided Outfit Recommendation with Preference, the authors tackle the challenge of personalized outfit recommendations. Imagine you're shopping online and want to find outfits that match your style and the current fashion trends. This research explores how to use large language models, LLMs, to do just that. LLMs are like super smart AI systems that can understand and generate human-like text. This research uses these LLMs to analyze fashion images, identify style elements, and recommend outfits based on your preferences. The researchers fine-tuned the LLM on a dataset of curated fashion images to make it better at recommending stylish outfits. They also developed a way for the LLM to learn from your feedback, like when you tell it you don't like a certain item or style. This means the LLM can continuously improve its recommendations and keep up with changing trends. The research demonstrates the effectiveness of this approach, showing that the LLM can generate more stylish and cohesive outfits compared to traditional methods. This research could have a significant impact on online shopping, making it easier and more enjoyable to find the perfect outfit. Imagine having a virtual stylist who understands your style and helps you discover new trends. This is the vision that this research strives to achieve. In Taken, a cohort of superior quality zero-shot speech generation models, researchers present a collection of models named Taken Audio designed for audiobook production. These models can create highly realistic synthetic speech without any prior training on a specific speaker, allowing for personalized audiobook customization. Taken TETS, a key model in the series, focuses on generating high-fidelity natural speech, while Taken VC excels at mimicking speaker characteristics. Taken morphing provides a way to control the speech's tone and rhythm to suit individual preferences. The research concludes that these models are effective and robust, as evidenced by their impressive performance in experiments. This research could have a significant impact on audiobook production, enabling authors and publishers to quickly and efficiently create customized audiobooks with various voices and styles. Imagine being able to instantly transform your book into an audiobook with your own voice or the voice of a famous actor. This technology could also be applied to other areas like virtual assistants, educational materials, and even video game character dialogue. In the research titled GRIN, Gradient Informed MO, researchers tackle the challenge of training mixture of experts MOE models effectively. MO models are known for their efficiency, as they only activate a small subset of expert modules for a specific task, making them computationally lighter than dense models. However, this selective activation of experts creates hurdles for traditional training methods like backpropagation, as the discrete nature of expert routing disrupts gradient-based optimization. The research proposes GRIN, Gradient-Informed MO training, which solves this problem by introducing sparse gradient estimation for expert routing. Moreover, the model utilizes parallelism to avoid token dropping. This approach allows GRIN to surpass the performance of dense models while being significantly smaller, proving its efficiency. For instance, GRIN-based MO models outperform a 7 billion parameter dense model while being only 6.6 billion parameters. The impact of this research is profound, as it paves the way for creating more efficient and powerful AI models, particularly in natural language processing. GRIN can potentially enhance various applications such as language translation, text generation, and question answering, leading to more effective and scalable solutions in these areas. In the research titled Almost Sure Convergence of Linear Temporal Difference Learning with Arbitrary Features, the authors tackle a long-standing problem in reinforcement learning. Imagine you have a robot trying to learn how to navigate a maze. It uses a technique called temporal difference learning, TD, to estimate how good each possible action is. But TD often relies on an assumption that the features used to describe the maze are independent of each other. This assumption is often not true in real-world scenarios. This research shows that TD can still work perfectly even if the features aren't independent. They prove that the robot's estimate of how good each action is will converge to a single, correct value even without the independence assumption. This is huge news for the field of reinforcement learning. It means that we can use TD in more complex, real-world situations without having to worry about this restriction. Imagine robots learning to navigate complex environments, like self-driving cars or drones, or even AI systems learning to play strategy games, all without needing that independence assumption. This research opens up a whole new world of possibilities for reinforcement learning and its applications. Wow, that was a whirlwind tour of some seriously cool AI research, wasn't it? And the best part? You're watching an entirely AI-generated video. No humans were harmed or even needed in the making of this analysis. Go ahead and check out the original research papers for yourself. The links are in the description. And hey, if you enjoyed this AI-fueled dive into the future, don't forget to give this video a thumbs up, subscribe to Singularity today, and let me know what you think in the comments. Until next time, keep your eyes on the horizon, because the future of AI is coming at us fast.